Good morning. This work introduces the notion of spectrum surveying with autonomous unmanned aerial vehicles and has been conducted by Raju Shrestha, Yves Tegania, and Sandeep Chapuri and myself. Before presenting spectrum surveying, let us briefly introduce what is a radio map. A radio map is a mathematical object, such as a function or a tensor, that provides the value of a certain channel metric, such as power or PSD, across space. So, for example, the map illustrated in this figure provides the received power in a certain channel across a geographical area with 3 transmitters. Clearly, this finds numerous applications in wireless communications. It can be used, for example, for finding areas with low coverage, controlling interference, etc. Nowadays, they are extensively used in the context of UAV communications. To construct these maps, one measures the metric of interest at multiple spatial locations and applies some interpolation or regression algorithm. So this paper proposes a scheme to efficiently acquire such measurements by means of UAV. To see why this is important, this video illustrates the typical process of collecting measurements, where a UAV follows a sequence of waypoints located on a rectangular grid. Observe that even after a large number of measurements, the estimate is still quite poor. In this paper, we address the design of a trajectory to obtain an accurate map estimate in the shortest time possible. So to this end, the UAV utilizes the previous measurements to determine which measurement locations are most. After summarizing the state of the art and describing the model, we will present the proposed scheme, which is composed of 2 parts. The first part comprises an online Bayesian estimator that utilizes each newly acquired sample to improve a map estimate and to obtain a metric of uncertainty at every location in the area of interest. The second part is a route planning algorithm that utilizes such a metric to find the best locations to measure. Finally, some experiments and conclusions. The literature of radio map estimation is already quite extensive. There are general purpose methods and even methods that utilize measurements acquired by a UAV. However, to the best of our knowledge, there exists no scheme that designs a trajectory for constructing a radio map. So as mentioned earlier in this work, a UAV adaptively uses the previous measurements to decide where to measure next, with the purpose of minimizing time necessary to construct a map with a target accuracy. To better illustrate the special features of the spectrum surveying problem as well as the proposed approach, we will focus on estimating power and service maps. However, our approach carries over to the construction of more general kinds of maps, such as PSD maps. So consider the typical propagation model where the power received at spatial location X can be expressed in terms of the transmit power, a free space loss component, as well as log normal shadowing and fading. Okay, so the measurements collected by the UAV at locations XT will be denoted by R tilde T and will be assumed to be corrupted by noise. For simplicity, we introduce some assumptions that are detailed on the paper and that essentially reduce the problem of estimating the received power to the problem of estimating the shadowing component. We consider 2 estimation problems to be solved in this first part. Specifically, given T+1 power measurements, the locations of those measurements, and the minimum received power to have service, we consider the problem of estimating the power at every spatial location, as well as the problem of estimating the set of those spatial locations that receive a minimum service, of the minimum service power. Service maps are of high interest in UAV communication, since UAVs to know where they have connectivity in order to plan their trajectory. So if we want the UAV to decide where to go next based on the previous measurements, it is necessary to maintain some form of uncertainty metric of the map estimate at every location. And the most natural approach is to adopt a Bayesian learning perspective. However, it can be shown that the MMSC or map estimators for these problems would incur unbounded complexity per measurement, and thus they are not suitable for an online operation as required here, right? So to bypass this difficulty, we will rely on a discretization of the area of interest as customary in the literature, as well as a conditional independence assumption that we will describe later. By arranging the power values at the grid points in the vector Rg, one can state the Bayesian version of these estimation problems as obtaining the posterior of the power and service indicators at the grid points given the measurements. The service indicator beta is 1 if at those locations where one receives enough power and 0 otherwise. In this work, the map estimate will be obtained as the mean of this additional distribution, right? And the variance, the uncertainty will be obtained from the variance of these posteriors here. As mentioned before, the batch Bayesian estimator for this problem has unbounded complexity per iteration. To circumvent this issue, we introduce a conditional independence assumption that essentially implies that all measurements can be discarded after they have been used to power at all the grid points. So that's the same to say that the posterior of the power at the grid points collects all relevant information from past measurements, okay? So with this assumption, one applies the machinery of Bayesian learning and comes up with this situation, which allows the UAV to obtain the posterior of the power map using the previous posterior, right? With every new arrival of a measurement. Once the posterior of the received power has been found through this algorithm, the service map can be obtained by realizing that the service indicator beta is just a Bernoulli random variable whose probability of being 1 equals the probability of the received power being greater than Rmin. This can be written as an integral of the posterior of the received power obtained using the algorithm that we described before. And this integral can be readily evaluated just by the means of the CDF of a Gaussian random variable. In this way, one obtains the probability that UAV receives service at every grid point, this PG beta, and this can be used in turn to find the probability at each location that is not a grid point. So, as indicated earlier, one needs an uncertainty metric to identify those locations where a measurement can be most informative in order to minimize the length of the measurement operation. So the question is how to quantify uncertainty, right? So for a power map, the most natural metric seems to be the posterior variance, perhaps normalized to lie between 0 and 1. For a service, observe that the most uncertain points are those where the posterior probability of receiving service is close to 1/2. Thus, an appealing metric to quantify uncertainty would be the entropy, right, of this service indicator. These metrics provide the uncertainty at each grid point. For quantifying how the uncertainty of the map decreases as more measurements are collected, one can just average the uncertainty across grid points. The second part of the proposed approach is to use this uncertainty metric to plan a trajectory along which measurements will be collected. Addressing the problem exactly is of course intractable, so a reasonable alternative is to adopt a receding horizon approach where a trajectory is computed every certain number of measurements. To decide where to go next, one can note that measuring at a certain point reduces the uncertainty there to zero. This uncertainty reduction can be seen as a reward that the UAV collects every time it visits a location for the first time. Thus, one can naturally formulate the trajectory planning problem as the so-called discounted reward version of the traveling salesman problem. The discount in this case is used to encourage the UAV to first visit those locations with highest reward, thus approximately minimizing the map uncertainty for a given measurement time. Still, the TSP problem, this traveling salesman problem, is NP-hard, so one needs to resort to heuristics. In this paper, we consider an approach where the UAV navigates to the location highest uncertainty and collects measurements all the way to that destination. And that follows to reach that destination is through a shortest path obtained through a standard shortest path algorithm, where the weights of the edges in the graph are chosen so that the drone avoids going through regions with low uncertainty. Okay. To see this algorithm in action, we consider a simulated scenario with two base stations. The top figure, top left, corresponds to the true map. This, since the locations and the transmit power of the base stations are assumed known, as occurs in real cellular networks such as LTE, one can just use the free space laws to obtain a coarse estimate of the map, which is shown here. This is the uncertainty, which, as expected, is low for points very far from the base stations, and also low for points very close to the base stations, because we know for sure that here we don't receive service, and here we do receive service. So this is not uncertain. So the uncertainty regions are these rings here. These now correspond to the service map. So this is the service map estimate, and this is the true service map. And here we will plot the uncertainty or total uncertainty versus time. So in this animation, we see we navigate to the areas of greatest uncertainty and quickly reduces the total uncertainty and obtains an accurate service map estimate, as can be observed by comparing these two figures. Here are the parameters used in the simulator for in the simulation reference purposes, and this is the illustration of how fast the error in the service maps and the uncertainty decay decrease using the proposed route planner, right? This mean cost planner, as compared to 3 benchmarks. Please note that it is not possible to compare with algorithms in the literature, because the proposed algorithm is the first of this kind. So to sum up, we presented a scheme to collect measurements for radio map estimation and autonomous UAV. The scheme comprises an estimator which provides power and service maps along with their uncertainty, as well as a route planner which targets those areas with highest uncertainty. Future work will target the more general estimators and more sophisticated heuristics for trajectory planning. Thanks for following this presentation.